Hello, everyone. In this session, we're going to talk about transformers. First of all, we're going to talk about the motivation of studying other advanced model architectures. And for our motivation, we're going to talk about machine translation. And to perform machine translation, the earliest model was in the form of sequence-to-sequence. And after we have a look at sequence-to-sequence models, we're going to have a look at some applications of seq2seq model, that is image captioning. Then we're going to talk about transformers. Transformers is generalized version of seq2seq models. The motivation first. What is machine translation? Machine translation is the task of translating a sentence X from one language, for example, English, and this language is sometimes called the source language. So sentence Y in another language, for example, Korean, and this is sometimes called the target language. In this example, the source language is in French. Yeah, this is French. And the target language is English. In this way, we want to translate one language into another. And we want our machines to perform this. And when it happens, we call this task machine translation. And what is statistical machine translation? It is to learn a translation model or the probability model. Given a sentence in one language, we want to maximize the probability of the correct translation in another language. First, we need a large amount of parallel data. What does it mean by parallel? We need to have pairs of sentences like English and French. And we need a lot of these pairs. Pairs of human translated French English sentences. And when we see the Rosetta Stone, it's written in ancient Egyptian, Demotic, ancient Greek, and they all mean the same things. And even in prehistory or earliest human society, we needed translation. And sometimes we say we want to learn alignment for statistical machine translation. And the second question we need to ask is how to learn translation model, this probability model, from the parallel corpus. We want to break it down further, and we introduce a latent variable A into the model here, where A is the alignment word level correspondence between source sentence X and target sentence Y. For example, this is written in German, and this is written in English. Morgen means tomorrow, and Flagge means fly. Ich means I. Nach Canada means in Canada, and zur Konferenz means to the conference. And what does it mean by alignment? Because each language has different order of words. In this example, we have subject, verb, and other components. However, in German, the verb comes first and then subject and other components. And when we think about Korean subject comes first and then other things, and last verb comes. So This kind of topologies are different from language to language. And what I mean by alignment is ordering the words in one language into another one. Okay, how do we, so it means we first translate each word into another language. And after that, we need to change the order. Then we can come up with the right sentence in another language. And that order is the alignment. And to translate one language into another, we need to learn this alignment. So the alignment is the correspondence between particular words in the translated sentence pair. And typological differences between languages lead to complicated alignments. And one thing to note here is that some words have no counterpart. For example, here, this word le is a spurious word. There is no correspondence word in the English counterpart. And this is not the only side case we need to think about. Alignments can be many to one. So these three words correspond to this one word in another language. And this opposite case, one to many, also happens. This implemented corresponds to these three words. And this is called one to many alignment. And we call this word corresponding to multiple words in another language a fertile word. In the previous case, this one is fertile word. And here, this one is fertile word. And there are also some cases where alignments can be many to many. In this case, we need to analyze the alignment in the phrase level. Here, 4 words correspond to 2 words. This is one of the cases of many to many alignments. And when you look at this alignment matrix, you can see multiple alignments. Okay, so the statistical machine translation model tries to convert one language into another. And sequence-to-sequence models tries to convert one sequence into another. Some nomenclature names these models as from sequence to another sequence, like this. However, we usually omit from here and call these seq2seq models. Okay, sequence to sequence with RNNs look like this. The input is a sequence and the output is also a sequence. For example, input is the source sentence and the output is the target sentence. And what we want to do is convert source input into target output. And how do we handle these sequences, 2 sequences? We are going to handle or process the input sequence with 1 RNN. And after that, we're going to manipulate the output sequence or generate the output sequence using another RNN. Therefore, the basic architecture of sequence to sequence consists of 2 RNNs. And here, the first RNN handling the input sequence is called encoder. This one receives the input sequence from the source language, like this, and it changes its hidden state over time. And after that, what we do is we receive this last hidden state and pass this last hidden state to decoder. And here, the first RNN was called encoder, and the second RNN is called decoder. And what decoder does is receives the start start token. And using this start token and the last hidden state, we usually don't have this context vector. However, you can put this context vector and it is initialized as the hidden state of the last time step of the encoder. And the different thing between encoder and decoder is like this. They're basically the same RNNs. However, in the case of encoder, the initial hidden state is in its initial state. So it's initialized randomly or initialized as zeros. However, for decoder, the first hidden state is initialized as the last hidden state of the encoder. That's the difference. After that, this decoder is similar to what we've done for RNN-based language model. Therefore, we feed the start token first and sample the first word. And after that, we pass this first sample as the next input and sample the next word. And we proceed with this schema until we get the stop token. And have a look at this. Encoder receives the time step input and the last hidden state. However, in the case of decoder, we receive the last output and the last hidden state. And you can put context here or not. It depends on you. It's up to you. And the very basic model does not contain context. However, if you put context here and concatenate this context vector every time with each time step input, then it's called picky sequence-to-sequence model. And why do we need to add this same hidden state, the last hidden state, multiple times? Because this hidden state summarizes the input sequence information. And as we set the first hidden state as the last hidden state of the encoder, it changes over time. And it could be a burden for this decoder RNN to remember the state of the input sequence. Therefore, we're going to separate this one with the changing hidden state. And we are inputting this encoded input sentence every time and help this decoder RNN remember the encoder state. That's the reason why we put the context vector here. And the problem is the input sequence bottlenecked through fixed size vector, because it has to memorize all the context of the encoder into this fixed size hidden state. And what if the time step is like 1000? And let's assume that our hidden state has the dimension of 128. In that case, it might not be able to memorize or summarize all the information in the input sequence into this small hidden vector. And that is a problem. And how can we resolve this problem? We can use new context vector at each step of decoder. And this is called attention. And we're going to talk about this attention in the later of this session. Up to this point, we've talked about the architecture of sequence-to-sequence. And once again, it could be challenging in language translation to memorize the whole input sentence in one hidden state here. And the performance can naturally decrease or deteriorate because this architecture is not suitable to memorize the input sequence. Okay, let's first implement sequence-to-sequence model, basic sequence-to-sequence model, and then proceed our discussion into attention models. In this session, I'm going to give you a working code example. And I summarized all the layers and base model we've implemented. When we implement sequence-to-sequence models, we're going to use the base model. What I mean by base model is our sequence-to-sequence models will inherit this base model. And this base model offers the functionality of save parameters and load parameters from file. That's all. That's not very complicated. Okay, this is just to avoid repeating the same implementation again and again, because save parameters and load parameters are used for pretty much every models we are going to implement. And we implemented these functionalities as base model. And after inheriting this model, the afterward models don't have to implement these two methods. Okay. And we've implemented this embedding layer, and we extended this embedding layer into time embedding layer. And we implemented time affine by extending the affine layer. And we also implemented the time softmax with loss layer. And there are some sigmoid and softmax functions. And we also implemented LSTM. And in the case of LSTM, we had to define 4 gates. And using these 4 gates, we come up with 2 states. The first one is hidden state, and the second one is cell state. And by introducing this cell state, we can make a gradient flow path, and we can avoid vanishing gradient problem in some sense. And although we haven't talked about time LSTM, this is just an extension of LSTM into time domain, time axis. And because we talked about RNN and time RNN, it could be quite intuitive to implement time LSTM from LSTM layer. Okay? Okay, that was some layers and base models we've talked about. And we also need to come up with some data set to test our sequence-to-sequence model. Here we are going to use the data set called addition. I'm going to show you a concrete example of addition data set. Don't worry about it. You just need to run this code, and you can access this data set and test or play with this data set. Okay, and we also implemented trainer to simplify the training process. The training codes are pretty much the same, and we don't want to repeat the same code again and again. So that's why we are implementing this trainer class. Okay, and we also implemented remove duplicate because we want to avoid updating the same parameters multiple times. And we also implemented clip gradients, and clip gradients are quite useful for LSTMs because LSTMs suffer from exploding gradients. And we also implemented some optimizers. And here we're introducing another function for evaluating sequence to sequence, because this trainer is really concerned about accuracies. However, what we want to do is somewhat different. And to accomplish our goal here, evaluating sequence-to-sequence model, we have come up with this evaluating sequence-to-sequence function. Okay, that was some utility functions. There were some utility functions. As you can see here, even though our model that we are going to implement is quite simple, however, to implement simple model, even though we're implementing a simple model, we need various utility functions and layers. And that's why we are using frameworks. Okay. Let's run this code first. Dataset, run. Optimization, run. Let's implement sequence to sequence model. How we are going to implement the sequence to sequence model is like this. We're going to first implement an encoder. Encoder is just a normal computational block. Therefore, it's going to contain an initializer like this, and forward method like this, and backward like this. And we're going to also implement decoder. And using this encoder and decoder, we're going to implement sequence to sequence model. Okay, let's first implement the encoder. And when we're implementing sequence to sequence model, we will inherit the base model. Okay, let's first implement encoder. We need to receive the vocab size and word fact size and hidden size. And after that, you just make alias for this word fact size and hidden size like this. And to make our code a little bit neat, we're going to make another alias like this. And we first need to define the parameters for our embedding layer. And we normalize for better optimization. And we also define LSTM parameters. And because we have 4 gates, we multiply h by 4 and divide this value by square root of b. And we also need to implement parameters for h, like this. And we also need to define the bias. Like this. Okay, then let's implement or define the embedding layer. We're going to use time embedding. And we define LSTM layer using time LSTM because we are dealing with multiple sequences. LSTM WX, LSTM WH, LSTM B, and we're going to set stateful false because we don't have to receive the same input again and again. Okay. This should be LSTM, not last. And we define our parameters as the same parameters of embedding layer and LSTM layers. And the gradient as the embedding gradient, LSTM gradients. Okay, Forward is very simple. We receive a sequence of input and pass this input through the embedding layer. Of course, we need to do that. That is very natural. And after that, we pass our word vectors, the embedded word vectors, to LSTM layer, like this. And update the hidden state, return the last hidden state like this. And how do you implement backward? We receive the age and set the gradient of the last component as the received DH like this, and pass this value to our LSTM layer, calling backward. And after that, we pass this value to our embedding layer, like this. Okay? Then how do we implement our decoder? Decoder is pretty much the same as the encoder. However, the difference is we need to set the first hidden state as the last hidden state of the encoder. And we cannot pass all the output at the same time. However, we need to generate the output sentence. Those two things are different. Those two things are what decoder is different from encoder. Therefore, we receive similar parameters: vocab size, word vec size, and hidden size, like this. And we abbreviate these values. We define embedding layer. LSTM WX. Square root B. And define WH. Set this value as H. Here H. LSTM bias. And we also need to define affine layers, because after we calculate all the hidden states and process the data, we need the score distribution among the vocabularies so that we can sample the right word. That's why we need affine layers here. Here we are using the vocab size. And bias for the affine layer. Okay, we need to define the embedding layer using the time embedding. And we define the LSTM layer using the time LSTM. And we set stateful as true. And we also define the affine layer using time affine. And we need to collect parameters and gradients. And we collect these parameters from the layer dot params, grids, like this. Okay, this is the implementation of the initializer. And we also need to define the forward method. This is pretty simple. What we need to do is set the state as the hidden state of the encoder. Therefore, we need to receive both XS and the hidden state of the last hidden state of the encoder, like this. Okay. And after that, we just pass through the embedding layer. And the LSTM layer and calculate the score using this affine layer. Okay, and calculating the backward is quite simple. We just first go through the affine layer because that is the last layer of this decoder. And then we go through LSTM. And then embedding layer, like this. And the last, the hidden state variant, DH, and we return DH. Okay, this is the implementation of decoder. However, we need another method for decoder, that is generate. Receiving the start ID and sample. We collect the sampled words in this sampled array list. And sample ID is start ID. And to our LSTM, we set state as the last state of the encoder. The difference between forward and generate is forward is used for training encoder and decoder. However, generate is used for testing, and the behavior is somewhat different. Okay, so that's why we are implementing this generate method. And how do you generate sentences? We pass this start ID first and sample the next word and use this next sampled word as the next input. And we get another sample using that next input. Okay? And after we collect sampled words, we return sampled list. Okay, this is going to be our first PPP exercise. Stop the video and take some time and implement this part. See you in the next video.